Welcome everyone. Today's lesson is about the derivative of a polynomial function. It's found in chapter 2, activity 2 or section 2, the derivative of a polynomial function. So in the previous class we talked about the power rule. We developed the power rule. We developed this rule by first principles of proving the existence or the occurrence of a derivative using limits. Okay, and we came up with this power rule. So the derivative, when I'm given a function, a single term, x to the power of n, my derivative is a n times x to the power of n minus 1. So we just take that power, right? We bring it down to the coefficient. We multiply it by the original coefficient if there is an original coefficient, and then the new term, the degree of the new term becomes n minus 1. Now, we didn't go through a proof. We just did examples, and we developed a table and showed this rule to be good and useful in finding derivatives. But we didn't develop a proof, and there is a really good proof in your textbook. There's one on YouTube that I've shared here with you. Okay, so we're going to get into the Smart Notebook lesson. Remember that you can find those lessons down here. Okay, and it covers Unit 2, Activity 2 today. So if you like to come back and refer to my Smart Notebook file that we'll do in a second, or the D2L class, feel free to do that. Okay, let's get started on the full lesson here today. All right, okay, so here's the power rule, and again, here's the YouTube video if you'd like to see the proof of this. Okay, this is going to be a big rule here, and really big, okay, rule, a main rule that we're going to use a lot in this course. Okay, simply define the derivative of a term. Okay, now the one rule that was on the D2L course was slightly modified. I included a coefficient. Okay, so my derivative function would be a n x to the n minus. Okay, so let's find the derivative of y equals x to the power of 5. It would be 5x to the power of 4. Sometimes we would write it as Leibniz notation. Okay. The square root of x is x to the half. Okay, so y prime equals half x to the negative half. Now, one thing I'd like you to get in the habit of doing is rewriting it back as a root and a positive exponent here. So this one would be 1 over 2 square root of x. So the negative 1/2, it puts the negative puts it down in the denominator, and then I introduce the root sign again. Okay, and it works for even strange exponents, really large exponents here. Simply just do the rule again. So the 100 becomes my coefficient, and my x to the power of 99 is my new power here. Okay, a couple of properties. Okay, a couple of properties and specific rules that are going to help us with finding derivatives. What about when the function is a constant? Okay, so constant, let's say y equals 3 in this case. We'll notice that since the derivative, okay, is just a slope, the slope of the tangent line, okay, the derivative of a constant is 0 because the slope of the tangent line is 0. Okay, so another example here, okay, if I have a function negative 10, okay, my derivative is just 0. Okay, constant multiple rule. This is the one, okay, that we did earlier here with the coefficient a. Okay, so I can simply just take the derivative of half a function where I can identify a constant multiplied by the function. Then the derivative of that is just the derivative of the main function multiplied by the constant. Okay, so in this case, f prime at x would be 3 times 2. Okay, and then x squared, right? And I know that to be 6x squared. Okay, this one sometimes it pays to, okay, write this as a power rather than a square root. Okay, and I can say g prime at x. Okay, this pen is acting quite a bit here. Okay, there we go. Okay, so that would be 3 and a half, and then x to the negative half. Okay, and again, please try and write my final answer back to the original way it was given in the question here. Okay, that's kind of the way the textbook shows those solutions here. Also keep in mind a couple other things I'm doing here is I'm using arrows to show sort of a thought process. If I have a function, okay, then the derivative is this. Okay, I use arrows just to show that process, right? I don't use equal signs here. Please don't get in the habit of thinking that the function is equal to the derivative. It's not. They're two different functions. And I can't just simply say like this equals. I've had students that do this. So if they, okay, and it's just a bad habit and form. They just go 6x squared here. And no, that's not the case here. So don't say that. It's a process. Okay. So the function is one particular function. The derivative is a different function. They're related, for sure, but okay, they're not the same. Okay, differentiate this one, the sum and difference rules, okay? And this means basically if I've got, okay, this is really for a polynomial. Okay, so if I've got a combination of terms, right, a whole bunch of terms, like in this case, this example 4 minus 2x to the power 3 plus x squared, the derivative, I can just take the derivative of each part. Okay, so the derivative of 4, okay, is 0. The derivative of negative 2x to the power 3, okay, is negative 6x squared, and then the derivative of x squared is 2x. Now, often we should just clean that up a little bit. Okay, drop to 0 here. Okay, no, not a problem. Let's think we're done on that slide. Yeah, we are. Yeah, so let's get on to, another example here, differentiate. Okay, again, we have them as reciprocal functions. So let's write them as powers. And then a plus x to the negative 5. Okay, therefore, my pen isn't cooperating today. I just want to, so let's get back to, so now I've got negative 1, x to the negative 2, negative 2, x to the negative 3, and negative 5, x to the negative 6. Make sure we get our integers right. We're subtracting 1 from a negative power here. So that's, okay, we go down to negative 2, negative 3, negative 6. Okay, let's rewrite this. Okay, again, the way it was sort of, okay, with positive exponents. So it would be a negative 1 over x squared. It would be a negative 2 over x to the power 3. And that would be a negative 5 over x to the power 6. And that's our derivative function. Okay, some applications of derivatives. Well, tangent lines. Okay, tangent lines are applications of derivatives. We find the derivative, we find the value of the slope at the particular point, and then we, okay, write the mx plus b expression. Okay, so let's see if we can do an example here. So I'm given a function, okay, and I'm given, okay, the equation. I want to find the equation of the tangent line at a particular point, okay, on this function, this graph, okay? So I can confirm this in Desmos and look at this, but the first thing I do is find y prime, okay? And I know y prime is actually my slope for the equation. All right, so let's just rearrange this a little bit. I've got x squared. I'm going to write this in a different way, and that 1 over x is just x to the negative 1. Okay, so my derivative will be 2x minus, and then a minus 1, x to the negative 2. Okay, well, that's a better way to write that is 2x plus 1 over x squared. Okay, so the next thing I do then, okay, I have a derivative function. The next thing I do, you may not like this notation, but I'm going to use it anyway, just to show you that the next thing I do is actually find the value of the derivative at the point x equals 1. Okay, so that'll be 2 plus 1, okay, or m equals 3. Okay, so when n equals 3, I have the value of my slope, I have a point, and I can put this into my slope-intercept form of my equation here. Okay, so y equals 0, m I just found to be 3, my x was 1, and that's going to allow me to find for the value of b here. way, and it allows me to write my tangent line. Now I'm going to go into Desmos and graph that. So I'm going to pause this and open Desmos up, okay, and see and just show you what this looks like here. Okay, here is my original function and my tangent line, and at the point 1 and 0 here. I'll just zoom in a little bit, okay, to see this. Okay, maybe zoomed in too much. Okay, so then there's my verified answer here. So back to my original question. Okay, and that was it. That's the steps for finding the equation of the tangent line, a common application for derivatives with these types of expression. Okay, so find the derivative of the function, evaluate the derivative of the function at the point, so finding the slope, the value of the slope at the point, or in this case it's x equals 1, and then taking that given point and the slope and finding the equation of my tangent line. Normals, okay, normals. Okay, so we've talked about normals in the past, and what we have to do in this case is that we just flip that equation of my tangent line around in value and get a different equation. Okay, so this time we're not finding an equation of a tangent line. We're finding an equation of a normal line. Okay, and again, that's just that negative reciprocal thing. Okay, so let's do it the same way. Okay. So we've got f prime at x will be 1. Okay. Whoa, I better slow down here a bit. Okay, I better do a couple of things here. First of all, it would be 2. So it's the negative 1. The way that's given. Sorry, I'm frozen here. Okay. Oh, there we go. I think we're good here now. Possibly. Yeah. Okay. So let's backtrack a little bit here. Okay. So I'm gonna go in and clean this one up a little bit here. Okay. We're still. Better check and see if we're still recording. Yep, all good. Okay. All right, so let's get back onto this here. Okay, so let's get ahead of myself here. Let's do a couple of things here first. Okay, so I rearranged this original function so that it had exponents here. So it's a 2 over x is 2 times x to the negative 1. Okay, so now my derivative is the derivative of x is 1, and I've got negative 2x to the negative 2. Okay, so that's 1 minus 2 over x squared. Okay, now I want to find the value of my function at 1 here, and that's going to be my slope. Okay, it looks like it's 1 minus 2 to negative 1. Okay, so that's my slope. Okay, this pen is driving me crazy. Okay, so now we've got our value of our slope and our point. Okay, but what I don't have in my point is my y value. Okay, and sometimes I'm not given that. Okay, and my x value is at 1. Okay, my y value would be so my point is actually, sometimes I just have to find out my full point, my x and my y values here in order to find this tangent line. Okay, now this is what I did in the past, but I've got to stop right here. This is the slope of my tangent line, but I want the normal. Okay, so I have to do something to find the slope of my normal line. So take the negative reciprocal. Okay, right now it's negative 1 over 1. Okay, the negative reciprocal is going to be Okay, 1 over 1, have to flip that and make the negative sign a positive. So it'll be 1. My normal will be 1. Okay, and that's, okay, I can simply just, okay, do that process here. So now I've got, okay, y equals 3. My slope is my normal, right? My normal. Okay, and that's 1. My x value is 1, and I've got a plus b. So that'll be 3 minus 1 is b. Okay, b equals 2. And my equation of my normal will be, okay, x plus 2. Now this one's worth graphing again. Okay, and I'm going to do that and get into Desmos. And I think I still have Desmos open. Yeah, so let's just start afresh here. Okay, so my original equation was y equals x plus 2 over x. Okay. And then my normal was y equals x plus 2. Okay, and that's this point right here at the point 1, 3. Okay, and again, that's not a tangent line, that's a normal line. Okay, so it's coming off my function, okay, at a 90-degree normal or perpendicular angle here. All right, let's roll with this. We're almost done. Okay, all good. Okay, oh, differentiability. We've talked about in 2.1, we talked about differentiability. We're going to review, okay, differentiability again here in this. Okay, there's a rule for, okay, the limit. Okay, the limit has to be continuous, or sorry, the function has to be continuous, and the slopes from the left-hand side and the right-hand side have to be equal in order for the function to be differentiable. Okay, so let's take a look at some weird functions before we finish this off here. We've got, okay, the cube root function, okay, x to the power of 1/3. And I'm also showing you, okay, x to the power of 2/3. These are weird functions. Now, we're not going to do any work here. I'm just going to review, okay, why these, okay, are continuous functions, but not necessarily, okay, differentiable. Okay, now in each case, okay, I've got, I'm just going to get rid of, okay, this. Now I just did this, okay, so, okay, that's all good. Okay, so what I do is I take the derivative, find the derivative first of this x to the power 1/3 function. And when I find the derivative, notice that I've got an x in the denominator, right? So the function doesn't exist at 0. Okay, there's a, okay, the derivative function doesn't exist at 0. Okay, and that's right in this area here. Okay, and that's because I've got an infinite slope situation. We talked about that as an example here. Okay, so the slope of my tangent lines, okay, at 0, okay, does not exist. Okay, and that's because of that situation right in here. Over here, similarly, the function, okay, x to the power of 2/3, when I take the derivative of that function, I get that occurrence, and it doesn't exist at 0 either, right? And that's because, look at the slopes of these tangents here, okay? On the left-hand side, it's going that way, and the slope of the tangent on the right-hand side is going that way. So there's no convergence here, and that's this cusp point here. So at times, we've got some funny functions that we've got to understand that they're continuous, okay, but they're not differentiable. So we're going to do one more example here, and it involves a piecewise function. Okay, so here's the situation. We've got, let's consider these piecewise functions in order to talk about differentiability of each. All right, so let's get rolling here. Here's our function. I've graphed it as well, too. Okay, so to find, okay, differentiability here, I'm going to, talk about, my derivatives. Okay, so if I have my function defined, okay, I can find my limits based on the same interval here, or sorry, derivatives based on the same interval here. Okay, and that's for x is less than, okay, and x is greater than 1. Okay, Okay, so I need to find the limit of my function as x approaches 1 from the left. Okay, and that'll be here, this line right here. So as x approaches 1 from the left, okay, I have that equal to, okay, I'll have that equal to, okay, 2, right? Okay, and the limit as x approaches 1 from the right of my function, okay, will also be 2. So this looks like it's, okay, just 1 second here. Okay, so this looks like it's, okay, okay. This is not, okay, so these derivatives, okay, exist and they have the same slope of my tangent here, right? Okay, but it doesn't look like, okay, it doesn't look like my limit, okay, from my original continuity check. Okay, so the limit, okay, let's just do my original function here. Okay, that was 1 minus, okay, the limit, okay, 1 plus my function. Okay, I'd have 1 here and I'd have 2 here. Okay, so it's not continuous. So we can see that on the graph because it's a jump, right? Okay, so it's not continuous in this case. Okay, so here's my function, okay, similar function, okay, but here's the situation here. So I've got, okay, so I've got a, let's do a continuity check first of all, okay, okay, this is for continuity, that's what I should have done in the first, okay, and I'm going to do my limits. That would be 1, okay, and the derivative of this one would also be 1, so it's continuous. Okay, okay, but I'm going to check for differentiability now. Now I have to find, that'd be 2x and 1 here, so that'd be 2, okay, and then the limit of my derivative function, okay, would be 1, okay, but it's not differentiable when these values are the same here. Okay, and then finally we've got, okay, this function. Now it, on the graph, it looks like it might be. It looks like the values are, okay, the same here. So let's find, that's 2x, okay, and this derivative will also be 2. Okay, so at the point, okay, so for continuity, okay, I'm going to do my limits. Use my original functions here. Okay, so that would be, okay, 1 and 1. Okay, so it is continuous. Okay, and now for differentiability, okay, do these limits. This is the limit as x approaches 1 negative of my derivative function. Okay, I'll use that function here. That would be 2. Okay, so the slope of my tangent is 2. And then the limit of my derivative function in order to check their differentiability is also 2. So therefore these are differentiable. Okay, and that tangent is there. Okay, so just to recap, okay, when it's not continuous, it's not differentiable, right? It can be continuous, but sometimes not differentiable. That's when the slope changes here, the slope of the tangent at that point. and then in this case here, it can be continuous and differentiable. Okay, we've got some homework questions, and the solutions are embedded in our D2L class, and let's get started. These are some good Gage's power rule, polynomials, and working on finding some of these derivatives here. All right, good luck.